So you're very familiar with the irrational number pi, right? You know pi is 3.14, and you know that it doesn't stop there, that number keeps going forever because it's an irrational number. And you probably know, of course, that pi has so many uses, and it's a beautiful number. And you may think, oh, pi is like the best irrational number out there. But running in tight contention for the best irrational number is actually the irrational number e, which you might not be as familiar with. E is a little less famous, at least in our math curriculum so far, but actually phenomenally useful. And has sort of slowly snuck into math history. So this lesson, I want to give you just sort of a little background to the number e, which we'll find out is around 2.72. So e, the first sort of appearance we know of it is in the early 1600s. A person named John Napier wrote down just a table of logarithms. And logarithms are essentially a way of undoing an exponent. And he made the base of this exponent this number, e, but he didn't give it a name. It was just sort of this table that he made, and nobody really cared. Next came along a person named Huygens, and so in Huygens was doing was actually looking at something very different from exponential things. He wasn't thinking about exponents at all. He was looking at the function y equals 1 over x, and so that function, it's a rational function, right, a fraction function. And it kind of looks like this. It has that nice sort of curve to it. And he was looking for the area between 1 and then some number over here, which you could say was maybe e. So the area between 1 and some number e, such that that area was actually equal to the number e itself. So he found that x value, whatever that x value is, which he didn't name e yet, but that x value was somewhere around 2.72, and that's the number that we now call e. But he had no idea this had to do with exponents. He had no idea this actually had anything to do with logarithms or actually anything of any practical value. He just thought, oh, that's kind of interesting. This area underneath the curve between 1 and some number here is actually equal to that number itself. Next, along came Bernoulli, and Bernoulli was doing something very different again. So he was actually looking at compound interest. And when we get to our financial literacy unit, we'll learn all about this formula here. So this formula is for A is the amount of money that you have at the end. P is the principal, so that's how much you initially invest. R is the interest rate, but you turn it into a decimal. It's the annual interest rate converted to a decimal. So if your interest rate is 4%, R would be 0.04. N is the number of compounding periods per year. So interest is not always compounded annually. In fact, often it's compounded monthly or semi-annually. So if interest rate is compounded monthly, then that would be N would be 12. There'd be 12 compounding periods per year. T is the number of years that go by. So that's just your general compound interest formula. But Bernoulli was looking at a specific math problem with that formula. He was thinking, well, what if I invest $1? So I make P just equal to $1 here. And I have an interest rate of 100%. So that means that R would be 1, converting that 100% into a decimal, right? And he said, well, what if I compounded this not just like every month or every day, but I compounded an infinite number of times. I make n actually approach infinity here. He wondered, well, how much would I have at the end of the year, right? If I could compound not just every second, every millisecond, every nanosecond, if I could compound an infinite amount of times in a year, how would that impact the amount I have? So a way you could simplify that formula, right? If my general formula was this, A is P times 1 plus R over N to the NT. If we sub in the fact that P is equal to 1 and R is equal to 1, and we make T just 1 year, then this formula will simplify to just 1 plus 1 over N to the power of N. as n is approaching infinity. We're trying to get an infinite number of computing periods in a year. To write this in mathy notation, what Bernoulli is trying to solve is what's called a limit. N can't actually get to infinity, right? You can't actually reach infinity. So we're trying to take the limit as n gets really close to infinity. So as n approaches infinity. So that's sort of the way we say that n is getting close to infinity, or as close to infinity as we can get of this thing, 1 plus 1 over n to the power of n. So that's what Bernoulli was trying to solve. He wasn't actually able to solve this problem. So he was able to prove that the number that you get when n gets really, really big is going to be somewhere in between 2 and 3. But he actually wasn't able to find out exactly what it is. But let's try approximating ourselves using just a really big n. So let's say we use n as like 1,000. You can pick any n you want. So we're going to do 1 plus 1 over, n's not going to be infinity, but we'll make it 1,000. That's a big number. And then to the power of n is 1,000. So try tossing that into your calculator. 1 plus 1 divided by 1,000 to the power of 1,000. You should notice you get something pretty close to 2.72. There's a bunch of other digits in there too. If you do a bigger number, here you'll get an even closer approximation of this irrational number, e. The decimals will always go on forever because e turns out to be an irrational number. But Bernoulli did not know he had found e. E didn't even have a name at this point. A little bit later, a person named Lydon, who's an extremely famous mathematician because he actually discovered calculus alongside Newton, was the other person who discovered calculus at the same time. And he finally gave this number a name. So this number 2.72 or 2.718, the digits go on forever. He finally gave it a name, but he actually called it B. So it didn't have the name E yet at this point. But definitely by this point in history, mathematicians are noticing that this is an interesting number. It's showing up in different places, in graphs of 1 over x and in problems involving compound interest and involving exponents. And it seems to have some cool properties. So people were looking at it a little bit more. Euler was the person who finally gave it its name. So he called it E, probably after exponential, probably not after himself, Euler, because he noticed that this has this cool connections to exponents, which is what we're going to use it for in this unit. And Euler was the first person to actually figure out a formula for E, so we could actually calculate it. And his formula is kind of cool. So it's a formula that actually involves a repeating pattern that we have to repeat an infinite number of times to get E exactly. But how it works is we take 1 and we add 1 over 1 plus 1 over 1 times 2, and then plus 1 over 1 times 2 times 3, plus 1 over 1 times 2 times 3 times 4. You kind of get the pattern here. There's actually a way of saying that mathematically. So this thing on the bottom here is actually called a factorial. So if I was doing 4 factorial, that would actually, so that exclamation mark there is actually a factorial. That would be 1 times 2 times 3 times 4. Basically, all the numbers from 1 up to this number itself multiplied all together. So what you can see here is I've got 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. The fast way of writing it is the sum. So this means the sigma symbol here is the sum from n equals 0 all the way to n equals infinity. So n equals 0, 1, 2, 3, 4, 5, 6, all the way up to infinity of 1 divided by n factorial. Let's actually try calculating this ourselves. Obviously, we won't go all the way to infinity, but let's try a few terms here. So the first one is easy, right? It's 1, and then plus 1 over 1. That's easy too. Plus 1 over 1 times 2, so that's plus a half. Plus 1 over 1 times 2 times 3, right, that's 6. And then plus 1 over 1 times 2 times 3 times 4, so it's going to be 1 over 24. Let's do another one. 1 times 2 times 3 times 4 times 5, that would be 120. We'll stop there. Let's see what you get. So when I add those all up, 1 plus 1 over 1 plus 1 over 2 plus 1 divided by 6 plus 1 divided by 24 plus 1 divided by 120, you'll notice that your number is starting to get closer and closer to 2.72. That's that special number, e, which is our irrational number. So Euler was able to actually prove that this was an irrational number, and he also discovered some more just really cool things about it. One of the things he discovered is called Euler's Formula. By the way, I know his name looks like Euler. It's not pronounced Euler, it's Euler. A lot of people get that mixed up. Anyway, that's Euler's formula right there. And it's a gorgeous formula that I love to use in physics all the time because it connects exponents to trigonometry. We're going to do a whole unit, of course, on trigonometry. But you'll find working with trigonometric equations can be really messy sometimes. And Euler's formula lets us take trigonometric equations and turn them into exponents. You can do calculus much, much easier with exponents than with trigonometric functions. And so Euler's formula will save your life in many a math problem in the future. A very handy formula. But the thing is, E is this mystical number because there's so much we don't know about it yet. We keep on it keeps showing up in other cool places, but there's tons of things we don't even know what they are yet. So e to the power of e, so 2.72, the whole irrational number, which I can't, of course, write out because it goes on forever, to the power of 2.72, that whole irrational number. We actually don't know if that's a rational number or an irrational number. Like, it looks pretty irrational. If you do it in your calculator, you get a decimal that goes on for a while, but we don't know if it goes on forever. That's not even proven yet. There's a lot we don't know yet about E. As you discover it, I hope you'll write to me and let me know what you find out when you become a mathematician.